Hello. This is video number 39. And we're doing something, yet again, completely new. But this is the last one that I think is really absolutely, positively, completely new. We're going to look at graphs. G-R-A-P-H-S. Graphs as a data structure. For us, the top of the line, the end of the road, the last of all the massive data structures. Featuring tons of terms, starting with graph itself. Definition. Graph as a data structure. A set of nodes. We know what nodes are. Or there are lots of different terminologies used. It's a set of nodes, or you'll see them sometimes referred to as vertices in the literature. V-E-R-T-I-C-E-S. Or some people like to spell that vertexes. V-E-R-T-E-X-E-S. Because each one individually is a vertex. I think technically that's supposed to be the plural. But I'll probably go with nodes. And a set of arcs. And there are alternative terms for the arcs. That was Michael. He doesn't bark for very long at a time, so I'm going to hope that passes and we don't have to start over. Arcs or edges, E-D-G-E-S, that connect the nodes. Now, I did that in several pieces, didn't I? Let me review the whole thing. A graph, in the context of data structures in computer science, a graph is a set of nodes and a set of arcs that connect the nodes. And you're thinking to yourself, well, we've done stuff like that. You could describe a linked list that way. It's a set of nodes, and the arcs, or those pointers in the pictures, those connect the nodes. Binary search trees. That's also a graph, nodes and arcs that connect it. And 2, 3, 4 trees? Yes. Everything we've looked at as a data structure so far in this course is a graph. There are all special cases of graphs where there are more and more restrictions on how the graph can be constructed. A binary search tree, only 2 outgoing arrows. A singly linked list, only 1 outgoing arrow. So we've gone from the very specific, very focused data structure to now this one, for our perspective, is completely general. You can have any nodes you want. You can have any arcs connecting those nodes that you want. So there's just nothing holding us back. Here's a fig way of example. And I'm going to call this G1. There are actually all different kinds of graphs that we could look at. And I'm not going to look at all of them, but I'm going to look at more than one. And this is the first one, G1. At the top, and the node labels, they're just arbitrary node labels. Don't try to attach any significance to those. I don't even know what this graph might represent. But at the top, I'm going to put Google. Google in a node. eBay over here. Yeah, it's just websites. That's what I got. And then Facebook. This is representative of the data or the value type value that's stored in the node. Over here, Amazon. What else we got? Wikipedia. I'm going to have to abbreviate that. Wiccup. Twitter. And, of course, Transy. Transy.edu, but I'm just going to put Transy. There. There are my nodes, or vertices, or vertexes. Here's some arcs. There's an arc from Google to eBay, an arc from Google to Facebook, an arc from Google to Amazon, an arc from Facebook out to Wikipedia, Facebook to Amazon. And then Wikipedia has an arc to Twitter, and an arc over to Transy. What else we got? Twitter has an arc to Transy, and Amazon has an arc to Transy. And I could have just made that up. I don't know why I was looking at my paper, but now it does match the one on paper, and I'm going to leave it that way. It might be easier for me. But there's an example of a graph. This graph, if you can see this part of the board over here, this graph is going to introduce a lot of terms. That's why I'm using this space over here. Is Undirected, U-N-D-I-R-E-C-T-E-D. And I'm not going to have room to write out the definition, so you're going to have to listen and maybe pause it. Undirected just means there are not any arrowheads on these arcs. If there are not any arrowheads on the arcs, and it's an undirected graph, it's not a one-way arc going one way or the other, then actually it's assumed that it can go both ways. In other words, this arc right here implies that I could move whatever sort of algorithm I'm doing that's moving around the graph, and we'll look at a few of those. But I could move from Wikipedia to Facebook, or wait, it's a two-way street. I could go from Facebook to Wikipedia. So undirected just means I can travel either direction along the arc among the nodes if I want to. There's one thing. It is unweighted. Well, what might a weighted graph look like? A weighted graph would have labels on the arcs as well as having labels on the nodes. This one is unweighted. They're called weights even if they're not numeric. I mean, maybe it's the name of the internet company that's going to give you the best deal on some of these connections that you surf all the time. I don't know. I made that up. But if we do have labels of any sort on the arcs, then all of a sudden it is a weighted graph rather than an unweighted graph. So the weight doesn't really, even if there are numbers inside the nodes, how heavy Facebook is or whatever, I don't know what that would mean, but it's not a weighted graph unless there are labels on the arcs. I don't know how to say that any other way. It is connected. Connected means there exists a path. That's another word. I'll put a red word up here. Path. We looked at paths in trees, I think. And it's the same thing in a graph. A path is just a way to get from one node to another. So I'll do this by example. A path from eBay to Wikipedia would be eBay to Google, I'll abbreviate, to Facebook, also abbreviated, to Wikipedia, all abbreviated. A path. Connected means any two nodes, throw darts at this and hit any two random nodes you want. There does exist a path between those two nodes. It could be just a single arc. There is certainly a path between Facebook and Amazon. There's also, let me see, eeny, meeny, miny, Google, Transy. Let's find a path between Google and Transy. I'm going to take the scenic route. I don't even have to take the shortest one. I could go Google, Facebook, Wikipedia, Twitter, Transy. Ta-da! I could list all that, and that would be a path. And all this is doing is trying to generically define these terms so that when we use these in the future, we all know what we're talking about. Why would we want a path between Google and Transy? Well, I don't know. That's irrelevant to this discussion. Okay. Now then, this also contains a cycle, C-Y-C-L-E. Oh, wait, is connected. Let me get rid of that. I'm going to put contains a cycle in just a minute. You don't have to erase it from your notes. Is connected. What would it look like if it were not connected, if a path didn't exist? I might have Yahoo. I'll add a couple of nodes and then erase them. I might have Yahoo and dictionary.com. There. If we consider this one big set of nodes and arcs that connect the nodes, it's still a graph, except this is considered to be a graph of disconnected components. That's the term that's used. And it's a surprisingly difficult problem to get a whole set of nodes in your data set and a whole set of arcs and to see whether or not the graph actually is connected, whether or not a path actually does exist between all the nodes. But that's beyond the scope of what we need, so I'm going to erase that there. That's not officially a part of G1. But that's how a graph could not be connected if it consisted of disconnected components. Okie doke. Now, contains a cycle was where I was going. And I'll do that by example in a different color. Red, I'll still use red. I'll put it down here. Cycle. Where do we want to start? Let's start at Transy. T-R-A-N-S-Y. Transy to Amazon, AMAZ, and we'll take our tour to Facebook, to Wikipedia, to Transy. I can skip Twitter if I want to. There's an arc that goes directly from Wikipedia to Transy. Transy, let me make sure I got these right. Transy can go to Amazon, can go to Facebook, can go to Wikipedia, and back to Transy. What's different between a path and a cycle? Yeah, path is like a one-way trip. A cycle is going in a complete circle, so to speak, a complete cycle. It starts and ends with the same node. And that is the only node that's repeated. We don't have any figure 8 cycles. So we start and end at the same node, and we go around using arcs. We don't use any arc more than once. We don't use any node more than once, except the start and ending point. That constitutes a cycle. What would a graph look like without a cycle? Well, one definition of a tree is it's an acyclic graph. It's a graph with nodes that are connected by arcs, but there are no cycles in it, even general trees, binary search trees, regular binary trees. None of the trees we've looked at have any cycles in them. There's no way to start and end at the same point, moving around to different nodes through all the place. What other definitions do we need? I'll do these by example as well. Now that you got all this, I'm going to erase it. This will be my little list of term and talk about it place. Two nodes. This will be by example. Two adjacent, ADJACENT, nodes. I bet you can guess this one. Let me see. Which one? Who's been neglected? Twitter. Poor Twitter. Twitter and Transy. Give me your best guess. Why do you suppose Twitter and Transy are defined to be adjacent nodes in this graph? Exactly right. There is exactly one arc between them. Twitter is adjacent to Transy. Wikipedia is adjacent to Transy. Amazon is adjacent to Transy. Facebook is not. Facebook is connected to Transy. It's not adjacent because they have to follow more than one arc to get from Facebook to Transy or Transy to Facebook. So there, a working definition of adjacent. This goes a little bit beyond what we need, but while we're talking about graphs anyway, a complete graph has, well, let's see, there's more than one way to define this. In a complete graph, I like this definition that I'm going to write up here. In a complete graph, every node is adjacent to every other node. Now, I wrote that so weirdly. Let me read it back and see if it makes sense. In a complete graph, every node is adjacent to every other node. Well, what does that mean? Here's a tiny little fig. I don't want to mess up G1 up here, our reference graph for the foreseeable future. Here's 5 nodes. And if it's a complete graph, every node's adjacent to every other one. There's an arc between every pair of nodes. And look, we have a Christmas decoration. This is 5 nodes with arcs from each node to every other node. And I don't know what else to say about a complete graph. A simple graph. We are, do I even want to define these things? Yeah, a simple graph doesn't have any self loops. We can't have any arc that goes from a node back to itself. That's a no-no. No self loops in a simple graph. And all of our graphs will be simple. No parallel arcs. We can't have 2 arcs between the same 2 nodes. See how that would complicate things? So we don't have to worry about any of that. We're going to stick with simple graphs that may or may not be directed or undirected. They may or may not be weighted or unweighted. And there are lots of other things we could say, but I'm not going to say anymore. I think that's enough to get the ball rolling with terminology and picture and example. So we'll pick it up again later. See you online.